In this one, we'll go over the storage issues and things that I've been facing with my setup. I've got essentially two units sitting in the rack, and they both look identical, but they do different things. So one of them is a 2U Supermicro server, which is a NAS, and this is running TrueNAS. And so, like we talked about last time, Avelino, you're running ZFS, and which essentially is what TrueNAS is running under the hood, except TrueNAS gives you essentially a pretty dashboard on top of that, and some other little bells and whistles, but essentially it gives you the management interface as a web interface instead of having to use the command line to get into everything. That being said, TrueNAS definitely does let you get into it with a command line if you need to. So one of these is the server itself, the NAS server. So like we talked about last time, it's got the motherboard, the RAM, all, the controllers, all that kind of stuff in it to run the actual computer portion of it. And it's also got 12 drive bays in the front of the unit. I also have, although it's not set up yet, below this is a JBOD. Not quite as elegant or monstrous, as you put it, as your setup. But basically, I have another one of these 12-bay units below it that's just a JBOD, so no computer portion, just drives. And I'm missing some of the hardware to be able to tie it into the server. So the setup for that is, to start with, essentially this. I've been running it off of 6 drives. To start with, is just a general like spinning. It's just spinning Rust. They're like 7,200 RPM, 6 terabyte drives, and I think I get something like 20 terabytes of storage out of it. So this is in RAID Z2, meaning 2 of these drives are parity drives. The other 4 are storage drives. Essentially, you can think of them that way. I lose 2 drives worth of space, but I also have a total of 3 drives that can fail before the entire array goes down and I lose all of the data. So 2 of the drives can go down and the array is still up and able to run. And then I have a really big backup drive, single backup drive, which is not best practice, but it also does a cloud backup right now too. So the chances of the array going down plus the backup drive going down plus the cloud going down is pretty slim. So I've got the stuff kind of backed up in 3 different locations. How does the saying go? If it's not backed up in at least 3 different places, your data doesn't exist or something like that. So I've got 1 spot on the main array itself, 1 spot locally on the backup drive where that data exists. And I've got another spot where it exists in the cloud. And this does automated backups, not only from this array to this backup, and TrueNAS facilitates that on an automated schedule. I've also got the cloud backups going up to Backblaze, and it's backing that up on an automated schedule as well. So like all my backups are automated. I technically don't have to worry about them, but again, there is as best practice. It's always a good idea to just go hit the restore button on your backups every so often and make sure that your backup system actually does restore the way you intended it to, because if you can't restore backups, that's essentially the same as not having backups at all, right? So, so this is what's going on so far. But I had a crazy idea that I wanted to play out here. And I got part of this going over the weekend. Actually, I got some really interesting results over the weekend that'll kind of lead to what we talk about here. But I've got a handful of computers that I use as actual workstations and stuff like that. So I've got like my main computer for development. I've got a computer over on the workbench behind me for doing electronics and things like that. I've got a laptop that I run, and hopefully this year I'm hoping to add another server. So hopefully for virtualization, fingers crossed. So we'll see how that goes. So that being said, I have a bunch of different systems that need to access data. And one of the things that I noticed I was doing is in basically like my my daily driving workstation here. I still have a single SSD, 4 terabyte SSD, and it's sitting in the computer. And I was realizing, well, if I've got the NAS, and I've got all, like, these systems all connected up to the NAS, why am I still running on a single drive when I could have that basically as part of some kind of array? So like the system right now has absolutely no redundancy. It's just a single disk sitting in this single computer. If I lose the disk, I lose all the data on the disk. So that was thought number one. So like, why not put a little redundancy behind that? Thought number two is I can probably squeak some extra performance out of this system by moving that drive to the NAS as well, or basically by moving that storage to the NAS. So that's it's a SATA drive. So it's got 6 gigabits per second that it can talk down that SATA port. And my storage network is actually all of my networks, but I have a dedicated storage VLAN that's 10 gigabits per second. So if I've got a 10 gigabit pipe directly back to the NAS, then that's actually got a higher bandwidth than the internal SATA port in the computer does. So why not take advantage of that greater bandwidth, right? So that being said, that got me thinking some things. And I guess I should explain the bandwidth thing too. So if these drives are capped at, say, 500 megabytes per second read and write for a SATA SSD, typical high performance SATA SSD on the consumer side, you're still likely to saturate a 6 gigabit connection, because that's going to be theoretically, what does that come out to, like 600 megabytes per second. So you're going to need roughly 1 gigabyte per second to saturate a 10 gig network. So the cool thing about ZFS, or by extension TrueNAS, is ZFS also has essentially a RAM disk in it. So anytime that you're reading or writing from the disk, it doesn't just go from the disk back up to the machine that requested it. It goes through RAM first, which means any of those any of that data that's already sitting in RAM gets served out of RAM first, rather than directly off the disk. So that's the thing that lets me take advantage of that 10 gig pipe. As long as the data is kind of off that SSD and it's warmed up in that cache, in the essentially in RAM, which ZFS calls the ARC. So adaptive something cache. I don't remember exactly what the whole acronym stands for. If it's warmed up in there, essentially you don't just have an SSD anymore at that point. You've got a RAM disk on the other side of your storage connection. So that's a powerful thing, because going out of accessing RAM is going to be way faster than any of the other methods that you have available. So if you can keep that data in RAM, you're going to have some really good access times and some really good throughput there.
What are some of the applications that you're currently that you're seeing an advantage from the ARC, versus what other applications would it not be advantageous to use?
Yeah, that's a great question. So one of the really big things would be running VMs. And that's actually a great reason why you want performance plus redundancy, or at least one of the things that I'm looking forward to. So basically for my hobby as well as for my job, I run a lot of stuff in VMs. I run a VM desktop for development, for example, and then as part of development, sometimes you want to emulate other systems or have a dedicated build box going somewhere to compile systems that you're working on or stuff like that. So you don't necessarily want those systems to be performant, so they're up and performing quickly as you're using them or compiling stuff or whatever. Like you don't want that stuff to be slow. And Although you can always rebuild a VM if it goes down, because again, like you should be doing those data backups. You shouldn't just have everything sitting there. So like in development, all that code is like committed and essentially backed up to places like GitHub or stuff like that. So you're not like losing work if the VM goes down. But if the VM does go down, because like you lose the drive or something, you lose time in rebuilding that machine. So, like at least you don't have the data loss, but you are losing time in the rebuild. From a hobby perspective, it doesn't sound as bad, but you are still ultimately like losing a good chunk of time you could have been doing something else. From a commercial perspective, like if you're, billing hours, which is, essentially like what we do, your downtime is lost income. So you really like don't want to have your VMs and stuff like that go down. You don't want to have your work machine go down essentially. So that's one of the cool things. The other advantages about moving all this over to an array is getting some of that resiliency in the with those resiliency strategies, which I've been debating, and so I have one set up already. But I'm not sure. In fact, I'm pretty sure I didn't land on the right one to start with. But there's a couple options there, and there's some interesting nuances in each of them. So I think that's one of the things to work through here. I guess the other thing to throw out there too is the other great use case for this is playing video games. Because everyone knows, if you're playing games, you just have to flex the fastest, the best specs and fastest drive load times and all that. I'm actually not one of those types of people who does that, but what I have noticed in actual performance right now is I am getting the stuff that does load from disk for stuff like that. I am getting like really nice load times. When you hit different parts of games that do that, so that's been really cool. And that being able to get that data out of the ARC, like there's a pretty big performance difference watching like load times and game assets, like all the 3D objects and artwork and textures and stuff like that, as that renders up. Like it has made a pretty good difference. So and the VMs boot really fast, so that's been nice. So yeah, I guess, Evelino, any questions or anything that I might have missed in that description that I should explain more?
Just one little note to make. Well, actually, if your VM, for example, typically the size of the VM can run, or at least for the type of work that we do, I'm assuming runs from anywhere from like 60 to like 120 gigs of VM snapshot.
Yeah, I think I've pushed about 250 gigs tops, but yeah, your range is pretty spot on for what they typically are.
Yeah, so that means that you could probably, depending on how much RAM you have, you can probably have a whole VM on the ARC, right?
Funny you mentioned that. Yeah, so I did start out the server with 64 gigs of RAM. As part of this upgrade, it's now at 128. So with the way that ZFS works that I mentioned earlier, with it being able to use basically your spare RAM as a RAM disk, yes, I can pretty much get an entire VM in RAM. And once it's warmed up in RAM, it does perform very nicely. I mean, don't get me wrong, it still performs plenty fine off. Like, I don't notice a difference when it's cold from the SSD being in my machine versus the drives being in the NAS. But when it's warm, like it's nice when it's warm. I'll say that.
But it kind of makes sense, right? That you're trying to push that off for its home to be CFS, because when you do load it and when it's warm, it's going to come through a 10 gig pipe versus SATA, right?
Yes, yeah, exactly. So theoretically, you've got an extra. Okay, so in theory, you've got an extra like 4 gigabits. You're kind of playing with there. In reality, the drives that I've got are 500 megabytes per second. So I think if you roughly do the math on that, you don't actually get the full 6 gigabit SATA pipe. You're actually getting something more like 5 gigabits per second. So just having it warmed up is already boosting that drive's performance by about 2 times. That's also rated from the drive's theoretical maximum, so you actually don't get 500 megabytes per second. I think I've got some benchmarks laying around that we can go through. But you're essentially getting something more like 450 megabytes per second, or maybe lower, depending on the types of like transactions you're doing on the drive, the types of read and writes. So yeah, you see a pretty substantial difference once you're hitting that ARC, that RAM disk. The other thing too that I think I noticed is probably worth throwing out there is when I was theorizing this in my head, I thought, okay, I'm going to load up a VM, and therefore it's going to put the entire, say, 64 gigabytes worth of VM in the ARC, and then it's going to use that to serve my workstation. If you think about it, though, it's far more efficient than that from 2 perspectives. So, number one, for anyone who doesn't know, ZFS has options where you can compress the storage onto your disks. So you're actually you've got some efficiencies there. So it's not running uncompressed like it might just in your normal desktop machine. You've got different levels of compression that you can run. And for these, I've just been running with the default of LZ4, and I haven't noticed a performance drop on it. I did some benchmarks with it on and off, and I think there is like a slight one, like maybe 50 megabytes per second. In reality, I can't feel it as a user. It seems just fine.
So the trade-offs are really good when enabling it, then, if we can't tell like the difference.
Yeah, and you can get some decent compression out of that too. So you can get like an extra like 10 to 15-ish% compression I've kind of noticed in the wild. So, over an array that might be like, say 10 gigabyte. Well, yeah. So if you've got like a 10 terabyte array, for example, 15% compression can get you a good chunk of extra space on that. So that can be kind of nice. The other thing I wasn't thinking of to start with until I saw it in practice is how is ZFS actually, what is it actually pulling into the ARC, and how does it decide what to pull in?
Oh, that's a question for me? I don't know. Like, I would just think like whatever you're querying for, and maybe adjacent files.
And so here's the question: what are you actually querying for in this workflow? And I'll give you a hint to make this look to my computer like it's an internally mounted drive. I've got this part rigged up over iSCSI. So I do have some Samba shares that I use for like cold storage and longer term backups and stuff like that. But as far as like the SSD feeling access, I've got that exposed through iSCSI. So what's actually going back and forth on the pipe in iSCSI? How does that protocol work, and what's it actually requesting?
I'm not too familiar with iSCSI, so I think that's an excellent thing to run through. At least protocol level. I do know how it works in general, but yeah.
Well, the answer is magic. So no. It's requesting blocks. So it's a block level. Yes. Mm-hmm. So the cool thing about that, if you're starting to put 2 and 2 together here, is you're not actually requesting like these 4 gigabyte or these giant files coming back for your VM. You're actually just requesting blocks. Mm-hmm. And so the other cool thing about that is, do you actually need every block of the VM to start the VM up? And no, you don't.
Right.
So
then that still begs the question, like, what is the algorithm for the ARC? What is the algorithm the ARC uses to warm up blocks? Depending, let's say like I request block 1. Is it going to warm up 2, 3, 4, and 5?
From what I understand, so I may get this part wrong, but from what I understand, I think ZFS has some intelligence where when it's working at that block level, it can be smart enough to know if you're pulling in like sequential blocks, it can know like, hey, I've got a request for this first one. I know that I'm going to need to like warm up the cache and like preload it with these next couple that come after it. If I remember right, I think it does something like that.
Okay.
I might be getting that wrong though. The short answer is, in practice, it's really fast, it works really well, and it doesn't actually use up 64 gigs of my RAM to load a 64 gig VM. So it's got other...
Is that also due to compression?
At that point, not really. The compression is kind of another thing. So that's like efficiency of storage on the array itself.
On the array itself.
Yep.
Interesting.
Yeah. So that part was a cool little rabbit hole to go down. I ended up running into some kind of interesting things to think about along the way. And I'm not 100%. In fact, I'm 100% sure I set it up wrong and not optimally to start with, and I probably want to redo it here. The question is, I've identified 2 alternatives that I can go to, and which one's really going to be the next best one to go with. So what I've got right now are essentially 5 open bays. So I populated these with 5 4 terabyte SSDs, the Samsung Evo 870s. So they are consumer SSDs, but they're the higher end of consumer SSDs. I did these in RAID Z1. So this gives you 1 parity disk or 1 drive that can fail, and your array can still run. The theory behind this, I know kind of like RAID Z1 or the hardware RAID 5 equivalent is kind of like frowned upon these days because there's better RAID choices to go with that give you, on one side, better reliability, on the other side, better performance. But I really didn't want to sacrifice too many of these drives to like parity or stuff like that. I figured 1 parity disk was probably fine, and I'm able to use the rest for storage. And since these are SSDs and pretty decent quality SSDs, I figured the likelihood of 2 of these drives failing at once would probably be pretty slim. And with an array of spinning disks, one of the high chances of failure there is when you're rebuilding the array. So like if you lose a drive and put another drive in and it has to rebuild the array, that puts a lot of stress on the other drives because they're physically moving and physically, going to read that data off the drives. So they're under a lot of strain for, depending on the size of your array, many hours or couple days, depending on how big it is. So you might actually have another one of these drives fail during that rebuild. I took a chance with an SSD since you've got no moving parts. Unless you just got really unlucky and got bad flash in it, which I'm hoping not, because these are at least the higher quality drives. I'm hoping there's a less likely chance that there's going to be a drive that also goes down during that rebuild process or that resilvering process.
Yeah, and at the same time, we can't compare it to spinning Rust, right? Because we don't have any moving parts, right? And that's some of the thought that was given to that decision, right?
Mm-hmm. Exactly. So if we kind of lay this out here, I'll just say this was RAID Z1 for this strategy. Maybe I should make this a little bigger so it's easier for people to see too. So strategy number one, I did some benchmarking on this as well. And here are some results. Let me just move this over and grab those.
Such a good citizen, Alex, capturing benchmarks.
I mean, I figured I needed to put like a little legitimacy to what I say, since I'm usually just full of hot air. But so I'll say I captured a couple different things here. Actually, let me just move this over. Let's let everybody see this. So I captured a lot of different things. And I ran several different tests with the RAID Z1 array here. I used Crystal DiskMark to do these, so standard benchmarking tool. I did a couple profiles, and so I did like overall RAID Z1 with the LZ4 compression, and then several different tests. I'll get into those. I did RAID Z1 with compression off, so theoretically the fastest, best performance that you could get out of the system. I benchmarked my internal RAM disk just for fun, to just get a comparison of what that would be. And I also benchmarked the main array here, the spinning Rust, with LZ4 compression, because I just had that on one of the drives already. So I wanted to see what that compared to. Spoiler alert, probably to nobody's surprise, it's really slow, as you would expect out of that. And then I benchmarked the Samsung Evo 860 drive, which is the one that's left in this workstation. So I didn't actually migrate that over to the array here. These are all 870s. I left the 860 in the workstation right now. I have future plans for that that we can get into if we have time. But I benchmarked that just in the computer here, so I have a baseline for that as well. So then going through each of these, there's a couple different types of benchmarks that Crystal DiskMark will let you do. So there's like the default performance, or the default benchmark, and it'll do sequential 1 megabyte reads and writes with, I won't get into this part too much, but 8 queues and 1 thread. Queues are essentially, I'm going to completely butcher this term, but it's kind of like how much stuff is like queued up or waiting to write to the disk. So sequential 1 megabyte with 8 queues, sequential 1 meg with 1 queue, random 4K reads and writes with 32 queues, and random 4K reads and writes with 1 queue. We also went into then like peak performance, which I might just ignore. I'm kind of thinking of ignoring the peak performance. I won't go into that too much, but it's exactly what it sounds like. It's just like, what's the best case scenario for that? Then I did the real world performance benchmark. And the catch here is you've still got that sequential 1 megabyte read and write, but 1 queue, 1 thread. So I think this is probably intended to emulate like one application just doing like 1 read or write request at a time. I may be getting this wrong, but that's just kind of what I've inferred from these benchmark settings. And then like random 4K reads and writes. So that could just be you're writing little files here and there. So sequential 1 meg may be a good example of that. If I've kind of got this concept right, might be like reading your 4 gigabyte VM files into the system in chunks. Although it's this sequential 1 meg, so think about reading lots of 1 meg chunks to get up to that entire file size. Whereas random 4K might be you're reading like settings files off the disk or something like that. Maybe single files of source code, multiple source code files from a bunch of different places to like, we'll say compiling your project. That might be a good good use case here if you've got like a Linux kernel you're compiling or something like that, and all those files are spread across little bits of your disk because you've kind of like downloaded and changed bits of the kernel source code, or whatever you've configured with it. When you go to run compile, it might be going from and pulling from a bunch of different places on disk to be able to find those files. So that might be a better example of that type of scenario. And then basically you've got the IOPS and the something in microseconds. So I assume this is access time of how long those operations took. And then IOPS is essentially how many of these operations could complete in a second. So read or write IOs per second is just what that means. So we'll come back, I think, to real world performance a lot in these examples. Those are, I think, the big benchmarks I did. So let me just close some of that out and go through some of these. So first of all, the old drive, or the drive being replaced. So these settings, I ran 5 passes of kind of like each one of these tests, each read, each write for each one of these categories. This is on a 1 gigabyte file that it's reading and writing each time, and then just the disk I'm running it on. So this was the Samsung Evo that was in the workstation, and this one pretty much matched the specs on the box. I think the box essentially says you get 500 megabyte reads and 500 megabyte writes, and we saw pretty much that performance. I'm going to call it good enough. And then we saw some other things down here, but probably the ones to point out were 10,000 IOPS on the read, 22,000 on the write, and kind of 93 microseconds, 45 on these access times down here. So that gives us like a benchmark of what a single drive in this workstation was actually doing. So I'll just put that over here for a bit. So if I go up to the same real world test for the RAID Z1 array running, we'll say no compression to start with. So that's kind of like apples to apples. So same settings, 926 megabytes per second on the read, 965 on the write, and basically 11,000, 12,000-ish IOPS, so we'll call that close enough. And then 10,000 on the write, so we'll call that half. So we've doubled essentially the read and write throughput and kept the IOPS the same on the reads. We've halved the IOPS on the writes. And we've also got a little more latency time, say like twice the latency on the writes. But it's pretty much comparable to what the read time was with the disk in the system. So things are mostly comparable, except lower IOPS here on the right, and double the throughput. I'll let that sink in for a second. I see something going through your head.
So the IOPS kind of makes sense on the right side of things, but the actual megabytes throughput doesn't make sense to me.
Yeah, and so what doesn't make sense? And so also just to clarify, if I didn't explain this was a single disk. This is that RAID Z1 array down here. So this is 5 total drives. One of them is parity, but we essentially have access to 5 drives at once. Okay, so that being said, so what's not making sense with this?
The IOPS is not scaling with the right megabytes per second.
Uh-huh. Do you see any? And I'll say you are definitely onto something fishy. There is something fishy going on with these metrics. Does anything else stand out at you?
Latency double there, but on the read, we're also getting double essentially.
Uh-huh. Do the read and write speeds look suspicious at all? And let me just go to another stat here. So here's the peak performance, which I said I was going to essentially throw away. But and actually, peak performance here was, maybe I should have looked at these a little harder. Peak performance off the RAID Z1 array was 113,000 IOPS here, 923 here. And then 1.2 gigabits per second on the read and 1.1 on the write. So this might show the scaling that you might have been expecting.
Probably. So on the middle image, we're coming up on the gigabit ceiling.
Yes, we've totally hit the gigabits, the 10 gigabit ceiling. We've hit that right here.
Yeah.
Yeah.
But oh yeah, that's it, right?
Yes. So that's
we
definitely
maxed out your pipe there.
Yes, exactly. We maxed the pipe out. So one of the other things,
is that what you were trying to hint at?
Yeah. So that was definitely it. There's also another trap in here. I don't know if you noticed yet, but it's something I'll definitely get into explaining.
No, I don't know what the other trap is.
And so I'll give you a hint. If you don't get it, we'll circle back around to it. But where we talked about this earlier at the beginning, but where is this data actually ending up? Is it
on your host system, your Windows system?
No. But on the NAS, is it actually ending up on disk? So I might have just spoiled it too much there. So
the ARC essentially is giving us illusions here.
Which in real life, though, so like it's giving us illusions on the benchmark, but in real life, it's actually giving us the real life performance we want out of the ARC. The catch is this benchmark, especially set to 1 gigabyte, on my ARC, that gigabyte is nothing for that ARC space. So it's just all sitting in the ARC. And we're essentially testing the performance of the RAM disk in that NAS. And we're just seeing what we would actually expect. We're seeing the 10 gig network pipe saturate before we actually see the NAS's RAM saturate.
Right. So now I'm curious, what other tests did you run?
Yeah, so I needed to figure out a better test to saturate the ARC and get the ARC out of the equation for benchmarking, right? So I at least found out, the good news is, in real life, for my real life use cases, it's fine. one gigabyte a day, it's fine. It's going to perform really nice. And it does perform really nice. I'll say that. It was running stuff pretty well. I was not disappointed with the performance in any way. But yeah, from a benchmarking perspective, I'm not actually seeing the true performance of hitting the disks, and I've got to get the ARC out of the way to be able to see that performance. So how might you get the ARC out of the way? Saturate the ARC. And unfortunately, well, I mean, this is real life, fortunately, but benchmarking, unfortunately, right? I've got 128 gigs of memory in the computer. It can use theoretically all of that for the ARC. In practice, it chews up about 10 gigabytes for the services that run on TrueNAS. And so it's got, it's still got over 100 gigs of RAM that it can use for the RAM disk. Unfortunately, Crystal DiskMark only lets you go up to 64 gigabytes total for your tests. But at least when it's doing like the read and write tests, well, it can still hold 64 gigabytes in there, but at least for the writes, if it's doing 3 writes at 64 gigabytes each, once one of those writes is in, the next write is going to kick out some data from the prior one, and the third one's going to kick out data from the prior one, and so on. So you kind of at least get that compounding effect that you really expect to see. So yes, the read megabytes per second are still going to get thrown off in the metric, but you're going to start seeing more of the writes that are hitting disk rather than the ones that are hitting RAM. And we do see that. So in the computer itself, we were getting like 469 over here. We are actually seeing that degrade because you do actually expect slower. Actually, this isn't, there's a white paper on this. This isn't necessarily true that you should see this, but we are seeing a performance hit of RAID Z1. So, you know. So once I saturated it there, that was basically the key to try to get these metrics a little more true to what was actually going on the drives themselves.
Mm-hmm.
And we can come back to that in a sec as well. Just to show what I benchmarked for. Actually, wait a second. I should go from the 64 gig test. So this was with LZ4 compression on. So that will slow down the read and writes a little bit as it's compressing and decompressing. If I just go to the 64 gig test with the compression off, it went from 271 to 375 on the writes. So on paper, there was more of a boost there. I think that's, roughly like 50 megabytes per second. In reality, I don't feel this in reality. But, if you're looking at the specs, yes, there is a little bit of a difference in the specs.
Mm-hmm. I'm bummed.
I know it's horrible performance, right?
Yes.
So I found a cool white paper that I'll pull up here that's helped explain some stuff, but also has me thinking of redoing this drive configuration a little bit.
Okay.
Let's see here. So iXsystems, the folks that make TrueNAS, put together this white paper. And essentially, it's a bunch of different ways that you can configure your drives. And there are other folks that have gone over like what this is on the web. I actually saw a video from Tom Lawrence from Lawrence Systems. His channel is really great to check out. He's got a pretty good explanation of everything in here. So I'm not going to repeat like that information, but I'm going to say like what I saw in here is how it applies to me and some of the decision, some of the ways this is shaping my decision-making process moving forward with kind of the next steps of what I'm thinking of doing. So there's a couple different ways that you can set up your system, like what we were talking about. And I'll just go over the ways before I go over the white paper. So we've got RAID Z1, and that's one of my drives is parity, and the other 4 are my free space, or are my storage space. So also going to a RAID calculator that you can find like this. If I just plug in 4 terabyte drives in RAID Z1, we'll probably end up looking at the cost in a second because that'll play into which solution you might actually want to go with as well. I've currently got 5 drives per RAID group, 1 RAID group. And if I calculate this out, I've got basically 15 terabytes of space. ZFS reports in TB bytes. So maybe I'll just stick with saying TB bytes here for this sake. But so I've got 14 available. Another way that I could do this, and so we've already determined that I'm doing the SSD route. I don't really need RAID Z2 for the extra redundancy or stuff like that. There are a couple things that I would be looking to get out of the array. One is, well, both kind of rely on more performance, but it's now a trade-off between performance, possibly slightly more reliability, and storage space. And each of the other two solutions here involve adding one more of these SSDs, which also means I have to pull them out of this unit and I need to migrate over to dropping these in the JBOD. So really, like, that main array is probably going to go down there, and like these SSDs are going to go over here. So this is why I'm going to have to hook up the JBOD to make this project work. This backup drive will probably go down there too in reality. And that'll actually get mirrored eventually, but not quite yet.
Okay, I have a feeling, I think I know where you're going, but go on.
Yeah, so one way here is, I'm going to throw you off for a second with RAID Z1, but this is really a 3x2 VDEV.
Yeah.
So that's really turning this into RAID Z1 there, RAID Z1 there. So each one of these drives becomes a parity drive. So I end up losing 2 drives to parity, but I've still got 4 drives for storage. So I'll put the parity drive in here just so it's visible too. And so I've got here 4 drives of storage, 4 drives of storage. So one extra drive lets me make 2 VDEVs. I'll go to the white paper in a minute, and that'll show the cool part about that. The other thing I can do, let's actually just make this like this, because this is going to make drawing the next bit easier. So I've got another 6 drives to work with, and we can do a mirror of 2 by, I think I actually need to do 2 by 3 because 2 by 4 is incredibly expensive. So right now I end up having to buy 1 more drive to pull this off any of these solutions. If I remember right, I think a 2 by 4 gives me the same amount of storage space, but I have to buy 3 extra drives. So I'm seeing what I can do with 1 extra drive. So each one of these becomes the same as what we've got with the parity drives. This isn't officially parity, it's actually a full-on replica, but you essentially lose 1 of these drives as a backup in each one of these VDEVs. So each one of these is now a mirror. A VDEV, by the way, is just a virtual group of disks in ZFS. And a ZFS pool, essentially your storage pool, is just made up of multiple VDEVs. So each one of these VDEVs is striped together, or in storage terms, that means you're adding the storage capacity of each of your VDEVs to get your total pool capacity. The advantages of VDEVs is you can configure the resiliency of each VDEV, and as long as all of your VDEVs stay up, your pool is up. If you lose a single VDEV, so we'd have to lose like 2 drives in one of these, as soon as you lose 1 VDEV, you've lost your entire pool. Like the data on your entire pool is gone. So just to clarify that. So these are a couple different options I've got. And this might be a good time to turn to the white paper as to why this option, don't get me wrong, this option, especially with the ARC, with a nice amount of RAM, is way more performant than just having not only way more performant, but also way more resilient than just having a single drive in my computer here. That being said, out of all of my ZFS storage configuration options here, it may not be the best solution. So taking a look at that from this perspective, actually, I've got the calculator up. Let's just dump 14 TB in here too. So this gave 14 TB. All right, so going over to this, there are some key takeaways from mirroring versus RAID. And one of the big ones here, so this is that's a 12-way mirror, so that's not a good example. But here's one of a 6x2-way mirror. So we've got each pair, let me just zoom in here a little bit. We got each pair of drives mirrored together. So this is a lot like what I did from what I showed earlier, except just to draw on the screen, we're just kind of taking like this chunk here. And then we're just ignoring this part that they have in the example. So I'd be building out essentially a 2x3 mirror or a 3x2-way mirror for that. So the takeaways from what you get from a mirror is you get more IOPS at the end of the day. You get the right IOPS of maybe I should actually back up and explain it from this. So if every single disk were mirrored together, you get the right IOPS of one drive. Whatever the right IOPS is of your slowest drive, that's what your write is. You get the read IOPS because all of these have the same exact data on them. You get the read IOPS of all of your drives added together. And then for streaming data, you could think of this as bandwidth down that pipe. Same thing goes for the streaming side of things. So for your read operations, you can read from every single disk simultaneously. For your write operations, you're limited by the bandwidth of the slowest disk in the pool because every disk needs to acknowledge the write before the write itself is acknowledged. Does that bit make sense?
Yeah.
Okay. So the tricks that you can start doing with any of these arrays is breaking them into multiple VDEVs, which is essentially striping or letting the system access multiple VDEVs simultaneously. So breaking this example up into basically groups of two, mirrors of two drives, the system can now access this simultaneously, this, and so on. So each one of those you've got simultaneous access to, which is great because now if you have a write that goes down into this one, only two disks need to acknowledge that write for your write to be acknowledged. Or, if a write is actually broken up to, say a write actually spans like 3 of these VDEVs, then, 6 drives need to acknowledge. But they can, each one of these VDEVs can be working in parallel. So you've got a bigger pipe there. So what you're now looking at is read IOPS and streaming read of the total of all of your drives. So you've still got the same benefits as we saw from the example above. With the write IOPS, each one of these disks, like they said above, does 250 IOPS. They pulled that number out of thin air, I think. So look at your own drive specs for what that is. In the benchmarks I just showed off, that was 10,000 IOPS or something like that. So your write IOPS is actually these groups of mirrors added together. So it's this plus this plus this plus this and so on. So that's kind of cool. You get a whole lot better performance out of a mirrored system, in theory. One of the problems with this, though, is storage efficiency. You're now burning one disk out of each of these mirrors in storage space. So you've only got 6 disks equivalent storage versus a RAID array, which we'll go down here in the document. Any one of the RAID options will make more efficient use out of your storage space on the disk. The takeaway here from a mirroring perspective is mirroring gives you really good performance. So if we go down to RAID, and they go over the different types of RAID options, but we'll kind of ignore these. So they go through RAID Z1, RAID Z2, and so on. But I'll just focus on the RAID Z1 side since that's what I'm doing in my specific case. So the catch here is with RAID, and it's weird that I didn't see these in my benchmarks, but actually, so they've got a RAID Z3 example here. So they have 3 different parity disks, just to explain this, with 12 disks total. So I'll just explain this this math down here that they've got, and that'll just set up kind of everything else I'm going to talk about. You're burning these disks in storage space. Like, you can't use those as storage. They're parity bytes or parity bits. So you have 8 drives worth of storage. In their example above, they said each one of these was 100 megabytes per second for streaming. So you can stream to and from this array, this RAID array. You can stream from each drive simultaneously. So theoretically, you're getting, if each one of these has 100 megabytes per second throughput, you're actually able to get 800 megabytes per second out of your array. It's weird that I didn't see this out of mine in the benchmarks, but I don't know what was going on there. But theoretically, this is how it works. The catch with the IOPS is you have the read and write IOPS of the slowest drive. And ideally, all of your drives in the array should be matched. So, so really, in theory, it's you have the read and write IOPS of a single disk. The reason for that being, it has to read the data. So the bits are striped across each one of these disks, bit 1, bit 2, bit 3, bit 4, so on. So it actually has to read each one of these bits off to make up a byte or however much is essentially striped across the disk. And then it also has to do the parity checks. So it has to go fetch every single bit off the drive, off every single drive, before this read operation can actually return. And it says, okay, this read operation has succeeded. So both inbound and outbound for reads and writes. So that's, on a RAID array, that's really limiting your IOs per second on the array, but theoretically you get really good streaming speeds out of it still. You probably note that these are still slower streaming speeds overall, I believe, than we saw from the mirroring example. But the other thing is the mirroring example had like a 50% space penalty because you're burning one disk to essentially parity on every single for the array. This is, I think this array, this was actually RAID Z3. I don't know why they said 2. Oh, this is the 6 wide Z2. So let me actually go back up here. There we go. These are the real numbers for this. So if each one of these, so 9 disks here, 900 megabytes per second. Each single disk in their example is 250 IOPS. So that's why you're limited to that. On this RAID Z3, you're 75% efficient in storage capacity rather than the 50% that we saw from the mirroring example. So as you go through different levels of RAID, you're basically more efficient than what you would be mirroring your drives, more space efficient. So you take a performance hit to be able to get more space out of your array. That's the trade-off. So if we've got, so here's a 3 wide RAID Z1 example, which is kind of similar to what I'm going to do, except I was just going to do a 2 wide RAID Z1. So what you've got here is Let me scroll up a little bit. Oh, they put the stats way up there. Okay, I'll stay down here and I'll just explain it. So if we've got 250 IOPS per drive, this VDEV can do 250 IOPS, and this second VDEV can do 250 IOPS, and these are additive.
Mm-hmm.
So we add both of those together. So our RAID now can do 500 IOPS. And for reading, we can read 100 megabytes, 200 megabytes, 300, 400 per second, because these parts are still additive for streaming. So if I've got that right, we should still be able to do 400 megabytes per second. And again, that's with their examples. My drives you saw were like 500 megabytes per second. So this would be more like 2,000 megs per second from the array that I'm actually looking at. And so if we were to take this back to, so let's say that was 500 IOPS and 400 megs per second. So if we were to take this back to the 5-disk array that I have right now, ignore disk 4 being parity. Disk 4 is actually data in this case. I can pull data off of 4 drives, so that's still the 400 megabytes per second. But all of this is one VDEV at this point, so that's 250 IOPS. So that's from their theoretical example. So I've got 2 things that I can do here. I can do this and keep a good chunk of storage space and double the IOPS. And just going back to the real world example here. So if I double the IOPS and I go back to the Samsung Evo that was in the system, it looks like in theory, this was the right IOPS in the system at 22,000. In the NAS, it's 11,000 in RAID Z1. If I do 2 RAID Z1 VDEVs, in theory, this bumps my write IOPS back up to that 22,000. And also in theory, should bump those read IOPS back up to 22,000 as well. It should double both of those. And since I'm still running 4 disks of data on each of these, also in theory, it should give me 2,000 megabytes per second on each of these. And so that should basically saturate a 20 gigabit connection.
Yeah, that's looking really good.
And I can multi-channel back to the NAS. I do have 2 lines that go back to the NAS. So if I multi-channel it, theoretically, I could actually saturate the drives with that 20 gigabit pipe. Or the other thing, like I mentioned in the future, is what this actually does is, and especially splitting the VDEVs up like this, is when I go to add in the virtualization server, or if I'm working on stuff on multiple machines at a time, say I got one machine compiling something and I'm doing, work on another, theoretically, that's where having those additional IOPS and having these VDEVs split would help, because one machine might be, and again, this is theoretical. In real life, it's striping between the 2 drives. But in theory, with those extra IOPS, I've now got, say, 11,000 IOPS for one machine to work with and another 11,000 IOPS for the other machine to work with. So it's parallelism, or that multitasking kind of ability of the storage solution here is better.
Yeah, CFS will have enough IOPS to cater to both machines running in parallel.
Yeah.
And everything that you just covered translates over to Rust, essentially. There is a catch, though, especially when you're doing a big Rust storage pool. It's easy to start and increment or increase your storage 1 VDEV at a time as you need more storage. But that means that you're filling up 1 VDEV at a time, meaning that you won't get the theoretical maximum out of these calculations in that scenario, because it's still only reading like a file. And this is only if it's like a Samba share, for example, not really if it's a iSCSI share. That just means that it's only going to be reading off of one VDEV at a time, because your files are on one VDEV as you've increased it. Obviously, that doesn't apply here, but I wanted to bring that up just in case.
Yeah, totally. Yeah, that's good. So the other side of this then is the mirroring. So if you want the best performance, mirror the drives, and that gives you a ton of IOPS.
Mm-hmm. That's also true with the regular traditional software, right? Like mirror is always going to be the most performant.
Yeah. So the challenge now is, my current solution gives 14 TB. The next solution, so this is RAID Z1, 4 gig drives, 3 drives per RAID group, 2 RAID groups. So I've still got 14 TB here to work with. So adding a drive, same amount of storage space, but doubling the IOPS.
Mm-hmm.
Next one with mirroring. So this is theoretically best performance.
Mm-hmm.
2 drives per RAID group, 3 RAID groups. I'm down at 10. We'll be generous and we'll give it 10 and a half. So I'm losing a good chunk of storage space, 4 terabytes essentially, or TB by doing that. The other thing to look at here is, now let's actually put in the drive cost. Because the easy thing to say is, well, just go in and just do the mirror. And actually, I'll just go back to the conclusions of this. The conclusion is, we'll do the mirror because you get the best performance, and then just add another 2 drives to bump the storage up to 14 TB. And just to go through this, because you heard me explain so like iSCSI hosting, VM storage, you heard me use a lot of these terms at the beginning of the episode here. And so the conclusion of this one is, we'll serve up iSCSI storage, blah, blah, blah. Basically, this says mirroring. If you can find
there, the more mirrors we have in the system, the more performance we can expect.
Yeah, here we go. So this solution from their white paper essentially says, if you're doing iSCSI hosting, VM storage, this happens to be database storage on VMs and stuff like that. But long story short, that kind of stuff, they're like, use the mirrors, go for the performance, take the storage hit.
Ouch.
Granted, that's not my only workload on this, but it's definitely a major one.
Uh-huh.
Here's the thing, though. So yes, ouch. The other thing is, so let's look at the actual cost. So the current cost of my current RAID Z1 solution is $2,500 in drives. To add the extra drive, I mean, no surprise, you're at $3,000 because another $500 drive right there. So going to the mirrored solution, I end up losing about 4 TB and having to pay another $500.
Mm-hmm.
To keep those the same amount of storage, I have to add another RAID group of 2 drives. So for that 14 TB, it's $4,000.
Mm-hmm.
So that's the catch here of, yes, that mirroring solution is going to be faster and more performant. But back to the benchmarks, what's my pipe going back from the NAS to each one of the other systems? 10 gigabits. And I could bump it up to 20 if I wanted to, but 10 gigabits for argument's sake. So out of this, if my performance numbers over here said, well, whatever, you remember the performance numbers. I'm basically getting, so I'm actually not using the saturated one at that point. My performance numbers are essentially coming off of, like, I'd be able to pull stuff into the ARC. So just to say, like, each of these are 500 megabytes per second that those drives are advertised at. So this is 2,000 megabytes per second. That saturates a 20 gigabit connection. If a 3x2 RAID Z1 set of VDEVs saturates a 20 gigabit connection, do I actually need to go to the mirrors to get more performance when I'm already saturating my pipe to one machine?
Right.
And I can actually fully saturate the pipe to two machines in that scenario. So, like, probably a realistic workload here is when I get the server up and running, the server will probably have a 4x10 gigabit pipe going into it. So it'll probably get, if I round robin it, it'll probably have 40 gigabits total. But just kind of like ignoring that bit, we'll just say, like, each host has a 10 gigabit connection. The server can be off running its own stuff, saturating a 10 gigabit connection, and my workstation could be saturating a 10 gigabit connection. And my array is 100% saturated, the storage array. It'll be just fine.
Mm-hmm.
I could throw another computer on top of this, and I'm probably not going to see performance problems. Like, it's going to, like, okay, yeah, 3 systems are now sharing it at the same time, but in reality, it's probably going to be, and remember, this stuff is also going up into the ARC. So in reality, this is probably going to be performing still way, way better than that single SSD in my machine. And this is also going to be performing better than this solution. The NAS itself also has 4 10 gigabit connections coming out of it. I'm only using 2 right now, but I can plug the other 2 in. They're already wired to go. I just leave them disconnected. And if I really needed the extra bandwidth coming out of the NAS, like, that's not going to be limited there. So I think on paper, and I guess literally on white paper, although it says, like, kind of the theory behind it says, like, mirror everything. Once you actually start breaking down, like, the cost and the trade-offs and how it's going to be used in the real world and stuff like that, I'm actually thinking that the most efficient solution here is probably the 3x2 RAID Z1 VDEVs.
Yeah, and that totally makes sense. The mirror option in the white paper is obviously more geared towards data centers, and where you definitely want the fastest hardware for your database, essentially.
That's another great thing that you just touched on right there. The white paper is also assuming production workloads.
Mm-hmm.
And I'm definitely not running, like a Google web server or something like that. Even my workstation, and if my workstation and, say, server were both running what are heavy workloads to me, those are still far less than data center workloads. So, like, that mirroring, the mirroring recommendation, I really feel is probably for, like, the production level stuff. Like, yes, if you're running your own AWS data center, or you're hosting your own, web services, web database, whatever, stuff like that, yeah, you probably want to mirror that. For home lab usage and basically running your own home system, home office, small lab setup off of this kind of thing. Sometimes having that extra space is
more valuable.
Yes, nicer for the price you're paying for that space.
Mm-hmm. It's pretty cool. Now the big question is, when are you gonna have time to be able to test that out?
So funny you bring that up. It means I have to get the JBOD in working order.
Oh, that's right. Okay,
yeah.
so.
But let me show you one more thing with the layout of this that I think makes this system hopefully better too.
Mm-hmm.
Oh, and I got another tool to show off also that's nice for everybody to see. But so if I do 6 mirrored disks, this is the other thing to think about. So like I have a total of 12 drive bays in one of these systems. So if I do 6 disks, so like what's my overall storage space that I can get out of this without having to expand to yet another JBOD? Because I only got so many PCI slots in that server or in that NAS. So I can only put so many controllers in it and run these drives at full speed before they start, having contention with each other. Which on an SSD, like that might be fine on the spinning disks here, but on the SSD pool, like I don't want drive contention. That defeats the purpose of performance.
Right.
So if I load this up with 6 drives like this, I could essentially run 2 10.5 gig pools or maybe 1 big pool, but like my total storage space here is to be 21 TB total that I get out of if I were to populate the entire system, or one entire chassis full of these. And so this is the awkward thing where if I went with like 4 of these to get like the 14 TB that I actually want, that's right. 1, 2, 3, 4, and now I've got like this lopsided thing in here, and then it's like, do I actually just array these out? And like, I don't know. I don't feel great about it. So the other option is if these are in, we'll say they're in groups like this. So if these are grouped vertically like this, and I put in just say like, so like here's a VDEV, here's a VDEV, and then another pool like VDEV, VDEV, or just, I don't know, maybe even 4 pools, but I'm kind of thinking probably splitting them. So now I've got 1 pool, 2 pools, that's 14 TB, and then I can add another 2 pools, do the same thing again in these bays. And now I've got 28 TB.
Mm-hmm.
So I get, just to round it out, I get almost another 10 TB of storage out of a chassis in this setup. And that doesn't feel like a bad deal to me.
Right.
Because what I could do, so like we were talking about like bottleneck, workload bottlenecks and stuff like that. If I wanted to, then with this array, I could have one of these pools. I could split this off into 2 pools, 1 pool, 2 pools. One of these pools could be dedicated to basically like my workstation and all of the stuff that like I work on around the home lab as a human. And then the other pool could be dedicated to like server storage. The other thing that I could do with the potential server setup is I'm not limited to just being locked into this storage scheme for life. If I add the server and I notice and I've got it like this, and it's like, hey, this pool is working out fine for like my workstation workloads, but the server just doesn't feel right. I could add in those mirrors like this for the server. So I could do my RAID Z1 VDEVs for the workstation workloads, and then the server workloads could be a 10.5 TB mirrored pool, assuming I'm still buying 4 TB drives at that point. So that's another option. So I feel like I've got a lot of flexibility in these routes.
Mm-hmm.
I also kind of feel like this one's the way to go with that RAID Z1 3x2 option there.
Yeah, I think with the current limitation being the 10 gigabit pipe there, that's probably your best bet right now. And in a few years, we're probably going to be able to find some NVMe JBODs or NVMe Supermicro chassis. So
yeah, exactly.
That sounds like a good upgrade to me at that point.
Yeah. So the other thing to know about, the other thing to know about is this storage pool or the reliability calculator. So this is cool to put some numbers into. So right now I have 5 hard drives per VDEV. It's RAID Z1, so 1 parity disk per VDEV and 1 VDEV total. So this is the current reliability curve or chance of failure for the current system that I have set up right now, this 5x1. And if I'm interpreting this correctly for failure probability here, the steeper the curve, the worse the solution is. So if I punch in the others here, we've got 3 hard drives per VDEV, 1 parity per VDEV, and 2 VDEVs. So this is the 3x2 RAID Z1 solution. And then we'll put in the mirrored solution, 2 hard drives per VDEV, 1 parity per VDEV, and 3 total VDEVs. And so configuration 2 is kind of in the middle there, the 3x2 RAID Z1. And this is one of the things that surprised me. I'm still not quite sure I understand how the math and statistics work out on this. But what's going on here is the mirrored solution is actually the most reliable, theoretically. The part that doesn't quite make sense in my mind is, so just to explain the mirrored case, you can lose 1 drive in any VDEV and your pool can still operate. Mm-hmm. So I could lose this drive and the pool still works. If I lose this drive, I've lost all the data in the pool. But I could lose this drive and the pool still works. And I could lose another drive out of the other VDEV and this pool can still serve data. So the weird thing, it feels like you're kind of playing like this game of odds, and this is where like I'm not good at statistics, so I'm probably like missing this of why this is more reliable. But to me, I see this as, so like theoretically you can lose 3 drives, but what I see it as is worst case scenario, you lose 2 drives and you're gone. If they're in the worst case scenario, if you lose 2 in the same VDEV, you've lost all your data. Over on the other side here on the RAID Z1 side, it's RAID Z1. So if you lose any 2 drives in a VDEV, all of your data is gone. So you can lose this one, your pool is still fine. Mm-hmm. If you lose this one, you've lost all of your data in the entire pool.
Right.
If you lose 1 drive here and 1 drive here, you're still fine. As long as you don't lose 1 other drive, you're good. So here you can lose 1 drive out of each VDEV and you're okay. But I guess still statistically, like if you happen to lose 2 drives in the same VDEV, you've lost all your data. Same thing over here. If you lose 2 in the same mirror, you've lost all your data. So yeah, this is where I don't fully understand the statistics of it, which is why go check out this calculator. It's pretty cool. It shows you these things, but apparently the mirror is more reliable, and I don't, because math, I guess is the short answer there. But yeah, at least my takeaway from this is, at least by splitting up my RAID Z1 array into two VDEVs and basically buying another drive to do that. Yes, I'm not as theoretically reliable as the mirrored solution, but it is more reliable than the setup I have right now. And I guess also just to throw it on here, just in case folks are wondering. So let's say I throw 6 drives as a RAID Z2. So you have 2 parity drives. I know we haven't really covered this at all, but just so you can see what the reliability failure chances for RAID Z2, really low. So if you're running a bunch of spinning Rust, don't use RAID Z1, use RAID Z2, I guess is the takeaway from that. But yeah, I thought this was pretty interesting, and I'm actually curious. You've got. Did you build any of your VDEVs differently, or were they still all what do you have? 8?
I have
8 wide VDEVs.
Yeah, 8 wide VDEVs, and I currently have 3 VDEVs, and we'll be expanding to a 4th soon.
You do yours RAID Z2?
RAID Z2.
Okay. So, I guess just to put this into perspective of what I'm running on the SSDs right now, so 511. So your curve for your VDEVs, granted you're running spinning disks, but your reliability curve is looking like this. And for my RAID Z1 SSD VDEV, it's looking like this. So that curve's looking.
Bump that total VDEV though up to 3.
Oh yeah, okay.
That's gonna change.
Yes. So this is a cool little calculator to play around with to kind of see that stuff.
The only solution there, the only way to get that curve back down would be to bump up the parity.
I think there's another way. So that's a really good test. Let's do that. So let's say you're running, what would you run, 8.3, or would you run something different?
Maybe 10.3 at that point.
Yeah, so if you run 10.3, you're looking a lot better.
That's expensive, though.
I think there's another option you could do here, too.
Yeah.
What if you ran 8.2, let's say 8.2.2? So now you've got better reliability. But now what if you ran 2 pools of 8.2.2? Because do you really need that much storage space in one pool, or can you start separating out which machines have access to what, and kind of how you've got your file share set up and that kind of stuff?
Right.
Basically your data sets and your zvols. So that's another thing to think about. For example, I do run 2 different pools. So I run by spinning Rust as RAID Z2, but the SSDs are only RAID Z1. So I do have 2 different storage pools set up there. And what I was talking about earlier, I don't have to follow the same format if I want to, or add to it if I set up another pool. I could set up a mirrored pool here for the server workloads, and that's totally cool. And it's a completely separate pool. It's on its own completely separate reliability curve. So yeah, that could be some interesting things to think about. Maybe you don't just have to keep adding VDEVs. Maybe you can split up the number of pools you're using.
Yeah, that definitely makes sense. And it might be a good idea to partition the data that way, so that one pool is just for VM and iSCSI in general, and then one pool is just for Samba sharing stuff.
Yep. That would also
be a pretty good strategy.
Yeah, that could split the traffic and types of traffic that hit each too, because we were talking about saturation earlier. So but yeah, that's this is what I've learned so far. I guess we're probably not going to get into building out the JBot or speccing the equipment to be able to get that controller up and running yet. But
I'm feeling it.
But it sounds like we've got a topic for next time.
Uh-huh.
Although I don't know, I'm kind of itching and might want to pull the trigger on that stuff before we meet again.
I mean,
unless
tomorrow.
unless I was going to say, unless we sneakily pre-record this episode and just release it later. So yeah, maybe I'll have to think about that one.
Yeah, just ping me.
Cool. But yeah, so I guess that's kind of like my walk through, my journey through all the stuff I've experienced so far, and kind of thought process of setting up this SSD array and kind of the differences between that and the spinning disks that I already had set up, and all the topologies and use case trade-offs and all that. And yeah, went on a bit of a research binge here, although probably not to the extent that a lot of people do. I think I did kind of a weekend binge on this to figure out all the information to make me feel comfortable enough. But yeah, there's definitely plenty of other resources out there from people who have gone over this stuff way more extensively than we just did here. And long story short, they're probably going to tell you to mirror your drives. But I would say, based on what I found, maybe don't always take that for face value, and maybe crunch your own numbers and kind of do your own critical thinking for your system and see what works best for you. Because like I found out for mine, like maybe I'm going to hit the performance cap before I really get the full use out of mirrors and stuff like that. So yeah. Well, cool, man. I guess this sounds like a good place to end this episode then, and we'll pick it up next time, possibly with a bit of story for how the JBOD goes, or I don't know. We'll see how itchy I get between now and then. Oh, cool. See you next episode.